loop reversal is an interesting again transformation, right? Again related to the cache in some way. All that it's saying is, if I have I is equal to n down to 0, right? If I had the memory and let's say that this was A0, A1, A2, A3, etc. As far as cache is concerned, this might all be one cache block, right? But what I might do is, because I read A3 first, it pulls in some data corresponding to A3, right? Next time around it goes to A2, it pulls in some other data corresponding to A2. They may not correspond properly to the same cache locations, okay? So it is possible that by reversing this, make it I is equal to 0, I less than, or I is equal to 1, I less than equal to n, I plus plus, right, and do this, you get the same behavior, but the way that memory is accessed changes and can potentially improve. It is not guaranteed once again, okay. But you have to be very careful. This and this look like they are doing the same function, because after all, if I look at what the for loop is going through, it is exactly the same in both cases. But the net result of doing this will be completely different in the two cases. In the first case, A of I gets a value from A of I minus 1. So in other words, A of n will get the value for A of n minus 1, A of n minus 1 will get the value from n minus 2, and so on. This will basically become a shift register. What will the second one become? What happens to A of 1? It gets the value of A of 0. What does A of 2 get? The same A of 0, right? So A of 0 gets copied everywhere, right? So this is an example where it looks as though the transformation is valid, but it is actually fundamentally changing the behavior of the program. So you can't just, it's not just a question of looking at the index variable and changing things around, okay. Loop interchange, once again related mostly to the problem of caching, right. What happens over here is, supposing you have a nested for loop and a two-dimensional array. The first question to ask is, how is a two-dimensional array stored in memory, okay. So supposing I have A over here, right, and it has rows 0, 1, 2 up to some, let's say 9, and this also has 0, 1 up to 9. So it's a 10 cross 10 matrix, right. How will this get stored in memory? It actually turns out that depends on the programming language that you are using, right, because there is no fundamental thing saying that this is how you need to store a array in memory, right. And furthermore, it turns out that C and Fortran use different techniques for storing it. They are called row major and column major approaches. So row major essentially says, I will store the entire row first. I will take A00, then A01, A02 up to A09, right. These are increasing memory addresses. Then will come A10, A12, A11, A12, etc. Okay. This is row major access. Instead, if I went by column, I would say A00 is the first one, but after that would be A10, A20, etc. Finally, I would go to A01, then A11, A12, etc. This is so called column major format. What is the difference? Again related to caching, because caches will always pull out blocks based on increasing memory addresses, right. So if you had it in row major format, then it makes sense for you to access the data in the row major format, right, access them one by one in that case. Now let us look at this loop, what is happening over here. You are going j is equal to 1 to m, that is the outer loop, and the inner loop is I equal to 1 to n, but what you are seeing is x is equal to a of 2j, okay. So every time that I go through the loop, right, in the for loop that I have over here, for the for I loop, right, I will first access A20, then A21, then A22 and so on. Sorry, this was actually a bad example. I think, yeah, I need to split this around. Effectively what would happen is, supposing I had something like this, for I is equal to 1 to n, for j is equal to 1 to m, and some function of, or rather I try to access the memory location a of I and some constant. Okay. What will happen over here is, I will first access a of 1, 2, then a 2, 2, right. What I would like to do, if I am writing a C program, would be A12, A13, A14, A15, those would be consecutive memory locations, but A12, A22, A32 are not consecutive memory locations. Right. So what happens if I switch the loop around and make it for j is equal to 1 to m, for I is equal to 1 to n, well, no, actually this will still not solve the problem. I'll end up basically with a strided axis, right. Right. So what does strided access mean? It basically means that I am going to access location this one, then this one, then this one and so on, whereas I would like to access them in consecutive order. If I can't access them in consecutive order, at least once I read them, I should use them through the entire inner loop before I go on to the next one. Okay. So if I can at least switch the values of I and j around, switch the order of the loops I and j, what will happen is, I will, when I do this, I will read a of I2, right. Sorry, this is again a bad example, I should have picked this carefully. Yeah, sorry. So actually what happens is, this is the even worse example, right. This one is better. Why? Because at least I am running through the entire for j loop every time that I do one read of ai2. So I do several computations before I read the next value of I. I can't get around the strided axis, but at least every time I read a value, I do several computations with it before I move on to the next one. Whereas over here, a changes on every iteration. Okay. So the order in which you write the loops can make a difference. Once again, is that valid? Are you allowed to switch the order of the loops around? That's something that you need to take care of. It's not always the case. Similarly, you might also have a situation where you have these nested for loops and you are trying to access some a of ij, that is the entire, it's the matrix itself that you are trying to access, all the elements. Okay. Once again, the order in which you are trying to do it, if your inner loop is going along rows, right, this is a bad ordering, right. The inner loop iterating on the rows means that on every iteration through the inner loop, the value of I is changing and I am accessing a strided element. I am basically jumping ahead n steps. Ideally what I would like to do is, I pick a row, go through the entire row, because that is cache friendly. So if I can switch these two around, this would improve the performance of this loop. Okay. These kind of things can actually be verified by writing the code corresponding to it. You can actually find that there will be a difference in the performance. Of course, it's not easy to create an example for this. The reason being, the cache memory used in modern processors is large enough that it's difficult to create a scenario where you would actually see these kind of differences. Okay. But when you write large programs and large, either signal processing or scientific computations, these kind of matters actually can become fairly common. Now, a word on dependencies, right? We need to understand this because it comes up both in the context of software as well as in hardware. So, Vivado HLS has a very strong usage of dependencies in order to do optimizations. Okay. What we have on the left hand side over here, for example, I have A is equal to 5, immediately followed by B is equal to A. Okay. This is a direct dependence, right, because if I try changing the order of the two instructions around, it will give me the wrong answer. Okay, that is one thing, it will give me the wrong answer. Okay. And not only that, A has to get its value, or rather B has to get the value only after A has actually been updated. I might be able to do constant propagation and so on, that is a different story, right, but there is a true dependency between the value of A and the value of B over here. Contrast this with what you are seeing over here, right. This, so in other words, effectively this is a true dependence. What we have on the right hand side on though is something else. I am saying A is equal to B and then I am saying B is equal to 5. In other words, I want to make sure that A gets the old value of B. Okay. This is not a true dependence. A does not care what the value of B is after the assignment, right. It only has to make sure that I do not end up using the wrong value. Okay. This is a so called write after read hazard. Okay. Why? Because I am writing after the read has occurred over here, right. Now, interestingly enough, you might feel that both of them are the same. After all, I wanted to take the old value of B, I want to make sure of that before I update the value of B, right. But it turns out that you can actually do a certain kind of compiler transformation which effectively says that don't update the value of B. Effectively what you need to think of is, when I assign B is equal to 5 over here, it effectively means that the old value of B is completely gone, I am never using it again. Think of this as a new variable, call it B1 and use only B1 after this. Okay. If I do that, the dependency is gone, A is equal to B can happen at any time, it will take only that old value of B, and anyway I am using B1 is equal to 5 and then using B1 from there onwards, it will give me the correct behavior, right. So, this is essentially something called single assignment operation, right. Any variable can be assigned only once. Okay. Now, for those of us who are used to programming with languages like C and Java, this is actually a bit counterintuitive. It is the exact opposite of what we are trained to do, right. What we normally think is, okay, declare a variable to hold a value, keep on updating the value of that variable, use it whichever way you want and so on. What single assignment says is, no, if a variable is a placeholder, but once you assign a value to it, it cannot change. So, the way that it is normally referred to is something called static single assignment, meaning that once it is assigned, it cannot change, right. It turns out that there are actually languages that make use of this kind of approach, right. They usually, the so called functional programming languages actually impose this as a constraint. They have a requirement that you cannot update the value of a variable. Okay. It does make certain kinds of computations harder to do, or at least harder to write the program, not harder to do for the compiler, but the benefits are actually quite significant. So, what happens very often is that the compilers do this automatically. They go through the values of variables, and the moment that you have updated assignments to variables, they rename them. Okay. So, you can convert it into something called a static single assignment form. The moment that you have static single assignment, all these kind of write after read hazards are gone. You do not have a problem that I might read the wrong value because I am updating it. I cannot update a variable. Okay. So, long and short of it is, both of these are dependencies as far as the program is concerned, the way that you have written the code. You cannot switch the order of the instructions around, but the one on the right can be fixed by changing the way that the program is written. Okay. The same thing happens inside this loop. What we are doing over here is, in both cases, in the first case I have b of I is equal to b of I minus 1, right. I need to make sure that I actually update I minus 1, and in the next iteration it is then going to update that into I. So b of 0 will get copied into b of 1, then into b of 2, then into b of 3, and so on. Whereas the right hand side is sort of doing the opposite. This is like the shift register, right. It is, I could in principle do all of these updates in parallel, whereas over here this has to be done sequentially, but this can be parallelized. Okay, provided that I read all the old values of b and update them into the new values of b at one shot, which, if you think about it, is exactly what a shift register would do in hardware. Okay. No, that is because in this case it is just b of 0 is being written into every array. What if it is a computation? So b of I is equal to some f of b of I minus 1. Well, okay, it is still a constant. So yeah, this is a trivial case. It's just an assignment where we have this. So my point is that it need not always be just an assignment into b of I. It can be something that is making use of the value of b of I minus 1 and doing a computation, which could change. Okay. In other words, yeah, what you raised is a good point. In the way that I have given the example, at least it looks as though I can just take b of 0 and propagate it to everything. You can construct more complex examples, especially once you bring in multiple variables over here, where I have some a of I minus 1 being assigned that is being used for b of I, right. So then I can have a slightly more complex dependency sitting over here, which is not quite easy to just get rid of by the compiler, but still has to be done sequentially because of the nature of the index variable. A related term, right, is something called a loop carried dependency, right, which basically says, let's look at this kind of, in fact, yeah, so this is an example of what we have over here. I am assigning b of I is equal to 8, and then I have a of I is equal to b of I minus 1 plus 10. Okay. I am trying to use what was there in the previous iteration of the loop, right. Effectively what it means is that the way that the code is written out right now, I cannot compute a of 1 until b of 0 has got a value. I cannot compute a of 2 until b of 1 has got a value. Okay. So there is a dependency that has been imposed by the loop. The way that I have written the loop, there is a proper dependency that is there from b1 to a2, b2 to a3, and so on. Okay. And I am updating the value of b of I, right, inside the loop over here. It will be used by a in the next iteration of the loop. Okay. So this, in other words, there is a dependency assigned in I, used in, okay, let me just change that, assigned in, let's say, k, and used in k plus 1. What I mean by that is, if I look at iteration number k, b of k would have got a value. That b of k would be used in iteration k plus 1 for doing the update of a of k plus 1. Okay. So there is a true dependency over here between these two assignments. Whereas over here what I have is, this is actually a loop independent dependency. I have b of I assigned over here, same b of I used over here. So there is no dependency between one iteration of the loop to the next, right. So this right hand side, all the iterations can in principle be run in parallel, left hand side cannot. Okay. And this loop carried dependency is something that you will actually come across quite often when you are trying to do synthesis using Vivado HLS. It looks at loops, it finds out that there is some issue with how the variables are being assigned and how arrays are being accessed. It will point out that it cannot do a parallel implementation of this, or it's not able to schedule it within the time that you wanted it to.